All right, guys. So at the current stage of the class, we have covered a few different data sets, answered a few different questions. We've predicted prices of housing in Melbourne. We've also built a model for predicting heart disease and then for analyzing handwriting. So we've done a few different case studies here so far. But today we're going to take a look at a different type of data set. So in this data set, let's actually go ahead and start loading it to see what it has. So we will let's go with import. You guys should already have access to the data. There are a couple of data files in the folder. We are going to be working with the transactions data. Okay, so let's bring in pandas. Last time we used NumPy, so let's bring that here as well. And for a little bit of visualization, we use the PyPlot library within Matplotlib. And we also used the scale pre-processing last time, so let's do that. All right, so the data set that we have let's call it retail for transactions. And in the data folder, so if we go up to the data folder, here we have one called transactions, one called customers, and one called baskets. So we're going to look at the retail transactions data, okay? So retail transactions. Yeah, okay. So let's go back to notebooks. Okay. So we want to load this data file. Okay, so the first, we've already started hitting issues. Let's see what it is. Oh, did I not put it in the right folder? Oh yeah. So I have it under the retail folder. Okay. All right, so now it says that UTF-8 codec can't be decoded. So this is a file read issue. My guess is that there's some characters in there in the data set that it can't read. So sometimes when you're dealing with some data files, it might have some special characters in it, which is not typical, but we can't control, the data in some cases, and so we just have to, especially if it's free form text or if it is some type of product name or something that it may have this. So let's go ahead and look and see if we can find a solution to this. So this is what we would typically do. The same error code, yeah. So let's just take this error code and look for, yeah, you see pandas read CSV, okay. All right, so what we're seeing is, okay, files with different formats. Maybe we can try a different type of encoding. All right, so when we're reading CSV, let's try it with this ISO encoding and see if that solves it. Basically, that's allowing the file to have other ISO characters as well. Okay, cool. So that took care of that. Let's see what the data looks like. Okay, so we have, this is retail transactions data. And as we look at this, so the first row here says that customer number 17850, customer ID 17850 came to a specific, for this store, this is all from one store, okay, or one online store. Purchased a white hanging heart light holder, 6 of them on the 1st of December, and each was a price of £2.55, and this is the stock code of the item and the invoice number. That means they bought this all together, right? That means this white metal lantern was also on the same invoice, and then this coat hanger was also on the same invoice. So we have the quantity and the unit price, right? So this is, imagine, and of course, if we go to the tail, so we are seeing a different customer ID and a different invoice, right? So of course, a customer can have multiple invoices. So think of this as one long 540,000 table with, each row being an item that was purchased, and it gives you what invoice it was on and who the customer was. So a customer can come multiple times to the store. So the same customer will have multiple invoices, and on each invoice, you'll have all the different items they purchased, right? So the question we're trying to answer here is, if we were given this data, so we're solving this on behalf of the store, okay? So we are the store, we're an online store, we're selling all these different things, and we have all these customers coming in buying this stuff. We want to segment our customers. So we want to know, can we group our customers into different groups? Can we say that, okay, these are, there's this set of customers here, all of our customers can, break them down into, these are the ones that maybe spend a lot of money, right? These are the high spenders. Then you have these other people that come to the store a lot. They're very frequent customers, but they don't spend as much money every time they come, right? And then maybe there are people that come a lot and spend a lot, right? Those would be called the whales. In the data science terminology, or just street language, you hear the term whales. These are people that come to your site or come to your service and they spend a lot of money, right? And they come often. And then you might also have a lot of people that just come to the store all the time, but they or they don't come very much, and nor do they spend very much money, right? So these are the people you may not want to waste too much time on. So we really want to try to segment the customers. So if we look at the data, we need to do some pre-processing, right? Because we're seeing that this is a little too granular for us. We've got, every item is a row in the table, and you have the quantity and the price. You don't even have like a total column, right? So let's do a little bit of data preparation, okay? So let's do some data preparation here. I apologize if I take time to switch here from code to Markdown, because I'm using this small Microsoft computer, which has a very small keyboard. Okay, so let's just calculate a total row amount. The row total. So basically we want another column that just gives us the quantity times the price, right? So that should be, which tells us what's the total for that row, and then hopefully we can aggregate that by invoice or by customer. So this should be pretty easy. We're adding another column called total, and what we're doing is we're taking our quantity and we're multiplying it by unit price. So just notice that whenever we code in for data scientific work, or just in general coding practice, we try to avoid using loops, right? Unless it is something that really can't be done through sets and vectors. So you see that here we're just creating one new column and we're setting it up. So in a similar way, we try to do all of our operations through vector functions or matrix manipulations, as opposed to putting them in loops. All right, so if we were to do this now, let's see. Okay, so now we have a new column called total, and it's basically taking the quantity and the price. So yeah, 2.5 is about 15. All right, cool. So we've created that. But now if we want to segment our customers, right now we have so many rows per customer, right? So we want to group this data by customer, And let's say that we want to plot. We want to take a look at, for every customer, what is the total amount they've spent, and how many times have they come to the store? Basically, how many unique invoices do they have? So something like this. So let me just draw this out real quick. So maybe we want to do something like this. If this is let's say this is the invoice count. This says, how many times have they come to the store, and this is the amount total, how much they've spent so far, right? So we might have some customers that come a lot of the time, or they come to the store a lot, but the total amount that they've spent is less, right? So they frequent, but they don't spend very much money. Then you might have some customers that don't come very often. That means their frequency is less, but they've spent a lot of money, right? And then you might have a bunch that don't come very much and don't spend very much, right? So, and then it'll be nice if you have at least a few up here, right? So these would be what we call the whales. And then you have, these are the frequent customers. These are the frequent, right? People that just stop by to pick one or two things. These are kind of like the wholesalers, maybe. These could also be wholesalers, right? And then these are just people browsing, right? Come and then come look at stuff and then leave. All right. So this is kind of what we're trying to put together. Okay. All right. So we need to do a group by, and so we want to group by customer, and then we want to be able to count or sum the total spend, and also count the number of unique invoices for that customer. Okay, so we're doing a group by. So let's see if we can do a group by here. Let's see. Does group by multiple columns and sum. Okay, so let's see. So here's a Stack Overflow question that tries to answer this. We have some data. They want to group by here they want to group by multiple columns. We only need to do that by one column, and then they want to get the sum of some others. So they have data frame.group by, and then you give all the ones you want to group by, and then you can use this .ag. .ag is a nice way to do it, right? So you group by this and then do a .ag, and then you say, how do you want to aggregate other columns, right? So they want to aggregate column 3 by sum and column 4 by sum. So let's try this, but remember we need to modify that a little bit. Okay, so let's say here we want to aggregate by customer ID, and so we got DF retail group by. We only need to group by one, so we'll pick that out of the list, and we'll just say group by customer ID, right? And then we want to aggregate this by the first thing we want to aggregate it by is let's say the invoice number, but we don't want to use sum. We want to do count, right? Count, and we want to count the number of unique ones. So if we go with Python count unique values in column, let's see, I think we used this once before too. You can do .n unique, but in this list we are looking at one column. So we can even just simply use a series. So we can do, and here we added numpy, so we can use a numpy function here to do the count. So here we'll say and PD, this is for pandas, and then we want to say series.nUnique, the number unique. We use this in the housing example, and yeah. So this says take this column and convert it into a series, and then find the number of unique ones in there. So there's different ways you could do this here, right? You want to be able to write how you want to aggregate it. So there's multiple ways to do that. And then we also want to take total. And now that we have numpy here, so we're just using b.sum. Okay. So these are, so we've generated this now. And maybe while we're at it, maybe we can also rename some of the columns. So let's define this data frame again, and that way we can do multiple things. Right? So here now we're going to do a rename. I'm going to rename some of the columns, and let's rename the because once it takes the unique, it's going to still leave it as invoice number. So we'd like to know that this column should now be called invoice count, and the total column should now be called invoice amount total. That's what we're talking about, the total amount of spend. And by the way, guys, I'm giving you some of the syntax, like even previously, because this piece of syntax is very much reused in many places. So if we know how to write that here, hopefully we won't have to waste a lot of time trying to do this over and over, or trying to learn this syntax over and over. Okay, and then because we are grouping, we always want to reset index. All right, this will make sure that the new table has a reset. Otherwise, it will try to remember all of these, and we need to set what those, and those indexes won't make any sense now that we've grouped it by. All right, and so drop the previous index. Okay. All right, so this should group by customer ID. You count the number of unique invoices for every customer, get the total spend by that customer, and then rename them as invoice count and invoice total amount. All right. Okay, so let's look at the new DF. Okay. Cool. So for every customer now, you have a row. We know that we could have put customer ID here as well if we wanted. Now we've got, so for example, this first customer came twice to the store and didn't purchase anything, came 7 times and purchased a total of 4,300 pounds and things like that, right? So now that we want to go back and analyze this, right? We want to go back and answer this question segmenting, and we want to try to get this. Maybe we can ignore people that never spent any money, right? If they come multiple times and they have never spent money, then maybe we can ignore that. So let's filter the data to only filter out anybody that just spent $0, or only look at people who've spent more than $0. So for that, let's say filter only positive invoices. Actually, let me call this retail transactions. So I'm going to rerun this here. We shouldn't have used the same name. We should use a different name whenever we redefine a table. Okay, so RTC is one. And so now we are going to filter out. So this is called Boolean filtering. And we can look this up, look this syntax up as well. Whenever we want to filter any table or column, we can, put a Boolean condition right inside the brackets. So for example, here and that condition can be anything. So that's why we're going to say this again. So give me within this data frame, filter out or filter in only the subset where invoice amount total is greater than 0. So this is the Boolean condition, right? This is saying, okay, if that is satisfied, get a subset of all of that from this data frame, right? And set it equal to this. Here I'm setting it to the same one. And so once we do this, if we look at the head of the table now, you see it dropped the one with the 0, right? And then let's just see. Okay, so we have now a total of 4,300 customers, and we're going to cluster them, group them put them in groups. Somebody actually has come to the store 248 times, and some people have only been there once, right? And on average, people come about 5 times. And in terms of spend, you have, the minimum spend is, very close to 0, maybe a few cents, and the most is, 2.79 times 10 to the 5. So that's like 27,000 or so. All right, so let's go now and prepare our data. Now that we've prepared our data, let's actually start putting it into a model, right? And then to try to group them. All right, and one of the things that we like to do is we want to scale the data, right? Because we have invoice count, in smaller numbers and amount totals in larger numbers, maybe. So let's scale it in. So I'm going to set my X to BFRDC, okay, because it only has 2 columns anyway. Let's go back there. Right, this is I'm going to be using both columns. Notice that we don't have a Y column, right? And so this is the first time that we don't have a label for the data. We don't have anything that says, like with handwriting, we have the actual number as the label, as the target. With heart disease, we knew that, whether the person had it or not. With housing, we had the prices. With tips, we have the tip value. Here, we have nothing. We just know that this is the data and we need to group them. Okay, so that's why we don't really have a Y. So we're in a different part of this class now where we don't have labels. All right, and now that we want to scale this, what I'm going to do is I'm going to say, if I just apply scale to the scale function, it's going to, let's see what it does. If I just apply scale to this and show my X, so it converts it into a series, whereas I'd like to keep it as a data frame, okay? So I'm going to go back to this and say that all of my columns should be scaled values of my columns. So I'm just taking my X, taking all of my columns, scaling them, and putting them back in. Okay. All right, so now when we look at X, right, it's in a data frame now, and you remember scaling basically puts it in the value between -1 to +1 with a mean of 0, okay, for every column. All right, so now that we've scaled it, let us now try to group them. So let's talk about that a little bit as to, so this grouping of data points is what is called clustering. Right? So the terminology for this is clustering. We want to take all the points and we want to group them and put all of these points together. The top left, all the ones on the top left, all the ones on the top right, all together. Okay, so let's take understand what is happening. So let's take a small example here. Suppose we have data that looks like this. Okay, suppose we have data that looks like this. We have a few data points. We have some data points here, and then we have some data points here, and we have some data points here, just to make things easy. We know that, when we look at this visually, our mind would basically say, all right, just by looking at it in 2 dimensions, it's easy. I'm going to group, this is one group, and I'm going to group, this is my second group, and let's put red, this is my third group, right? We do that visually. And this is fine in 2 dimensions, but when we have more dimensions or when we have tons of data, how do we do this? So one of the methods, and you guys might have heard of this before, is goes this way. So first of all, we pick, and let's say we know that we want to group this into 3 groups. Okay. If we knew that we want to group it into 3 groups, then we randomly pick 3 points. Okay, we randomly select 3 of the points among the ones that we have here. So let's see if we pick use a new color. Okay, so suppose we picked okay, so we picked this as one of our points, and we picked, so we had green and red, right? So, and then we picked this as one of the points. Remember, this is random, okay? So we randomly among all these pick. So maybe we picked these 3 points randomly. All right, so randomly selected 3 points because we know that we want to group them into 3 groups. That is something we already know. All right, so now what we do is once we have selected these points, we take all the remaining points and assign it to the nearest. So we're going to take this one and see among these 3 which is the closest and assign it to that. All right, so this is going to go here, 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 here. This point is going to go here, here. This might go here. This might go here. And then, right, all of these probably are going to come to this one, right? Okay, so now that that's happened, so we've essentially created one cluster, one on this side here, right? This is 1, this is 2, and this is 3, which we obviously know is not the best, right? So then what we do is, so let me take some of those out, okay? All right, now what we do is, within each created cluster, we now calculate the mean of that cluster, okay? The mean of all the points. So in this case, if it's 2 dimensions, we take, the X mean and the Y mean. And so now, so basically we're trying to find the center of this cluster, right? So let's say the center is here for this cluster, and for this one, the center is here. And for this one, of course, most of the points are up here, so the center is probably somewhere there. And that becomes our new center, okay, as opposed to these random points, okay? So now this just goes back to becoming a regular point. This goes back to becoming a regular point. This goes back to becoming a regular point. And now you repeat the process. Now we take all the data points again, but now we are trying to see which centroid, this mean centroid, it is closest to. So now what we will see is, so in the second iteration, all the points are going to, these points are going to be assigned to this one, this, right? So that cluster somewhat stays the same. Here, this point, now they're coming to this new cross in the middle, but you see that since this cross, the red crosses all the way to the right, this one's going to be assigned, some of these points are going to be assigned to the green cluster, even though you see that this point here was the primary point for the red cluster, but now it's actually a member of the green cluster, right? And then these points kind of come to the red cluster. So by using this centroid and by taking the mean of these, so what we've done here is we've created this as the cluster now, this cluster, and this whole thing now becomes part of the green cluster, which is kind of what we wanted, right? Visually said. So this method of finding the mean and using that mean to cluster them as we would have expected is called k-means clustering. And k is the number of clusters. In this case, k is 3. So we know that we want to put them in 3 clusters. So, and then you keep looking for the mean once you go through an assignment. And then, so the next step here is, so, I mean, we may not be done, right? We might need to, again, calculate the mean. The mean might have shifted. So in this case, now that, you know, all the points are here, the red mean might shift, you know, somewhere here now, right? And the green mean might shift somewhere here, and so on and so forth, right? So how do we know when to stop? Okay, so one of the methods that is used to know when to stop is by looking at the size of each one of the clusters, and that is measured by, you know, some people call it variation, some people call it distortion. So if we measure the total variation, so let's see here, for the blue cluster from the mean, right, this is the total variation. For the red cluster, here's the total variation, and for the green cluster, here's the total variation. So if we take, let's call it V1, V2, V3, and then we take the sum, right, V1 plus V2 plus V3, this is the total variation we have in each iteration, right? So in each iteration, we have the total variation. So what we are going to find that is that in the first iteration, so in iteration 1, where we had this red point here, and you know, we had that big red cluster on the right had a very large variation, right? The size of that cluster was very large, and so, you know, this variance, if we were to plot the variation, then that variation was high, and then over time it's getting reduced and reduced and reduced, right? So we want to stop when the variation doesn't help us anymore, right? That it's not reducing very much anymore. So we're monitoring the variation, and when it reaches a certain point, it's not going to reduce anymore. This can also, this variation can also be used to figure out what k should be. Suppose we don't know that we want 3 clusters, right? Then what we can do is we can plot the variation, right, with respect to k, right? So if, you know, when k is 1, if I put everything in one big cluster, the variation will be very high, right? And then if I have 2 clusters, then obviously it would reduce significantly. And maybe when I get to 3 clusters, it reduces more. But then when I add more clusters, at some point in time, that change in variation is not going to be very much, right? So then it's going to start to to even out. So in this curve, we want to find what is called the elbow of the curve. And now sometimes you will see the same curve drawn the other way like this, and they'll call that the elbow. But that's just basically the inverse of the variation, okay? Or reduction in variation or whatever, right? So either way, you're looking for the point in the curve at which the relative improvement of adding another cluster is not that much. So it didn't really help to add another whole cluster. It didn't reduce the variation very much, right? And just to take this to the extreme, if the number of clusters is actually equal to the number of points, so in this case we have 4,000 some points. If you had 4,000 clusters, of course the variation is 0, right? Because there's no variation. Every point is its own cluster. But on the other hand, if we put everything in one cluster, then the variation is high. So we're looking for this elbow point, right? And there are some metrics, and let's just talk about one of these metrics. So if you were to, let's say we measure this variance or variation. We don't want to use the term variance. Let's say we want to compare, or we want to calculate this variation in a way that we can sort of over time and easily measure it. There's an interesting metric. So let's, if we were to take, let's say we were to take let me do it for blue here. Okay, so we have the size of this cluster. Okay, so if V is the diameter, maybe this is kind of the radius. So let's say we have, this is A, which is a measure of the size of, or the variation of the blue cluster. And if we draw this other line, which is goes all the way from the center of one cluster to the center of the other, to the edge of the other cluster to this point, okay? So if we measure A versus B, so A says how big is my current cluster, B is how far am I to the boundary of the other cluster. So what we want is, if we had to calculate a metric, we want A to be small, right? We want that to be as dense and tight as possible, and we want B to be large, right? We want it to be far away from the other clusters. That's what at least we do mentally. So one way to calculate that is if we were to write this out as B minus A, right? So the larger this is, the better, right? But then we want to normalize it. So we divide that by the max of A and B. So if we were to calculate this, and this is large, that means we know that these clusters, it's a good clustering because we're very dense and we're far from the others. Okay, and so this metric, this is called the silhouette score. Okay, so we may be able to use this metric, and we want to try to have a high silhouette score. And so we might vary different values of K that gives us the best silhouette score. So at the elbow would be the point where the silhouette score is the highest, right? Because we may not always be able to look at it in 2 dimensions, right? So we just want to calculate the silhouette score and then show that it is highest. All right, so let's do this real quick for this example, and then we'll go into some other methods of doing it. Okay, so let's see, build k-means clustering. And let's go here, see if we can go, sorry. Let's go here and say sklearn k means let's take a look at that. So it's within a library called cluster, and it's called k-means, so that's as clean as it gets. K is given by n underscore clusters, and then there's a few other parameters that you could use. And here, let's look at the syntax. They call the k-means function. There's a dot fit, but then we don't really need to. Yeah, so there's a dot fit, and then if you call the dot labels function, it gives us what cluster each of the points has been assigned. And then if you have a new customer that comes in our case, then you can call the dot predict function as well. So this is a new customer. And then if you want to find the centroids, you know, the mean points that we showed, you could do the dot cluster centers. But because we are not really doing any predictions, we're not trying to say that if a new customer comes, we're going to try to predict which cluster they belong to, which we could very easily. But in our case, we just want to group the customers we have, so we just need to call the dot fit and the labels function. So let's take this, and we know that from cluster it is in k-means. All right, so say from sklearn dot cluster import k-means, and we'll use our terminology MDLKM k-means clustering for retail customers, and our number of clusters, let's say it's 3. Maybe we're looking for the 3 different groups, and state 1. Let's call the fit function separately because that's what we're used to. So this was the define. Then we do fit. We don't really need to do a predict here, so we'll just go with fit x. And then let's call this the k means labels and set it to this so that we can use it later. Okay. All right. So once we've done this, we would have built the models and we have assigned the labels to each point. Okay. All right. Let's see. Maybe we want to look at this a little bit. So let's just do a scatter plot. And for our x-axis, we're going to use x invoice count. And for the y-axis, we're going to use invoice amount total. And then we know that because we have the labels now, let's just put them on in color. Okay, use labels. And just say, just so we know what each is, X label is invoice count and Y label is invoice total. Let's just put a title so we know this is K means clustering. All right. Cool. So this is our two-dimensional chart where invoice and amount total, and we asked it to put it into 3 clusters. So it's taken, so there's one cluster down here. These are probably the people that don't spend very much, but don't show up very much either. Then you have this layer of people that they spend a little bit more and they come to the store a little bit more. And then you have sort of these points on the outside. These are people that just happen to be spending more money. And you have this one here that spends more, but also comes a lot. And so it's a good initial clustering. You might be able to do different marketing engagements with these people down here, saying, hey, why don't you come more often, because they obviously don't come very often. Maybe give them some deals. Then you have these folks that are coming very often, but we want to just try to get them to spend more. So maybe different types of marketing engagements for them. So that's the type of case we want to, we might use this for. Okay, but how do we know? And we can calculate a silhouette score for this, right? Let's calculate the silhouette score. So, there was silhouette score. So let's go here and then say learn silhouette score. All right, it's in metrics, and you provide you just provide X and the labels. All right, so from sklearn.metrics for silhouette score, and we want to calculate the silhouette score. We just needed to pass in X and the labels, and here we called it k-means labels. So can you just use that here? Okay, so it has a silhouette score of 0.87. So the higher, the better, right? So we can kind of imagine what we're going to do next, right? We're probably, we could probably, iterate through different values of the number of clusters, which is basically iterating through the different values of k, and trying to figure out which of them gives us the best silhouette score, right? So for that, let's put this inside a function. We've done all of this before, so I'm just gonna zip through it. Let's say this is the function for k-means clustering. Define cluster k-means and then give X and K now, because that's going to be an input. And our model is going to take K for the number of clusters, and then we're going to want to return the k-means labels, right? That's what we want to return. We want that to come back. And maybe we can also calculate the silhouette score while we're at it in here, and then pass that out as well. So let's do this, put that in here. Let's call it k-means sil score. So let's give the labels and the actually, maybe we don't need all the labels. We'll just go with the silhouette score. Yeah, we'll just return the silhouette score. All right. So we've now defined the function. So now let's iterate over different values of k to determine the best silhouette score. So here for k in a set, maybe we'll start with 2, 3, 4, 5, 6. And these should be, based on what you think, your business is, right? And then let's say, so k-means sil score. We want to get that from cluster k-means X and K. We're passing in X and K. And then maybe we can try to print. Let me print, say K Okay, and then the value of k, and then tab to the next. Then we provide the, say, SIL score, and then give the k-means SIL score. Okay, for that one. All right, so let's see if this works. Cool, so we're saying that actually you don't even do very much better from a cluster size of 2, and that maybe makes sense, right? This divider here kind of might seem a little weird. So we may end up putting more in one cluster and then maybe carving all the others out here as a different cluster. So from this we would basically say that a 2-cluster model is probably the best, right? But you can also go ahead and tweak some of the other parameters of the k-means, and then try to tweak your model to see if you want to get something better. All right, so this is one way of clustering, right? But then let's look at this, in a different way. Here we basically took all of our data points, and right. So here we took all of our data points and we assigned, we created, in iteration 1, we created clusters, and then we calculated the mean, and then we went towards the mean, right? And we had to iterate through all of this to try to do this, and then you had to calculate silhouette score, and then repeat the process multiple times to try to get the value of k. But here's a different way of doing it. What if we so I'm gonna draw this again. Draw the same plot again, and yeah. So we had a few points. We have a few points up here, and we have some here, and then some here, right? Okay, so another way to start is to start from the bottoms up. So think of this like a top-down approach. We create the clusters, and then we try to modify and tweak the clusters to get better. And in this method, what if we assigned each point to its own cluster in the beginning? So in our example, if we had 4,000 points, that means we have 4,000 clusters. And so basically each one of these is its own cluster. And then after that, in the second step, we start each cluster would be connected to the next closest cluster. So initially this point and this point are its two clusters, are each a separate cluster. So these two get put together, these two get put together. This is closest to this is closest to this, right? So all of these kind of get paired with the closest one, right? And you see sometimes you're going to end up, depending on the order in which you do it, you might end up with a few that are outside, that don't have a pair, right? But then you'll have, this is a pair, and so on and so forth. So then what? Then you merge them together again. So you'll put these two in a cluster because they're closer, these two in a cluster because they're closer, these two, and this is alone in its own cluster, so because there's, and then you'll say these two, and that bites off, right? And then, so in this way you see, and then now you only have 1, 2, 3, 4, 5, 6, 7, 8 clusters, and now you bring it closer to the next one. So this is connected with this, and this is connected with this. This is connected with this. So now you have 1, 2, 3, 4, 5 clusters, and then you go one more further, and you say, okay, this cluster is now closest to this one. This is closest to this one. Oh wait, there's one there. That's close to that, and now you have 3 clusters. You see how you ended up in the same result, right? we ended up in the same result here. This ended up being one cluster. This ended up being another cluster, and this ended up being another cluster. But then we could have kept going, right? We could say, okay, this whole cluster is close to this one, and this whole cluster is also close to this one, and then so we just have one big cluster. So what have we done here? We started from every point as if it was in its own cluster, and then started pairing them up with whatever is close by. So now you have, as if you took all of your data points and divided by 2, right? And then you start pairing them closer and closer and closer. So this is kind of what's happening. So you imagine that you, in one dimension, right? Just imagine that this was a one-dimensional problem. You start pairing these points up with whatever is closest to it, and then you start, putting this and that together, right? This and this together, this and this together, right? And then you start putting this and these two together, and maybe this is kind of far, so you put, this and that together, and then you bring these two together, and finally you bring this together, and then it's all one cluster, right? So this methodology is called hierarchical clustering, which makes sense because you are clustering them in a hierarchy. You're starting from everything and then you're going up, and you don't need to know how many clusters you should have, right? So in this case, what would have happened if we had drawn this chart out on the right for the data on the left, it would have been something like this. And in this chart, right? So this is what we're seeing here is the distance, right? How far it is to the others, and you didn't need to know K, you didn't need to know how many clusters, but from looking at this chart here, by the way, this chart on the right is called a dendrogram. So you look at the dendrogram and you say, where can I draw a line across that very cleanly shows that there are groupings? So if you draw it down here, you see that this is somewhat, this is very short. This height here is somewhat short. So there's not much difference between this and this. There's not much of a distance. But you see from here to here is a big. So you might say, you know what, I think the best place to cut this off is here at this point. And so because I have 1, 2, 3, that means I should have 3 clusters. Okay. So this method is called hierarchical clustering. You don't have to provide K, and by looking at the dendrogram, you can figure out what the cluster should be. But then this distance can also be measured via the silhouette score, right? The silhouette score still can be calculated, and so you can still use that as well. So let us try to do that now. Try to do hierarchical clustering in our data. So let's go with sklearn hierarchical clustering. All right. So hierarchical clustering is actually in sklearn, they call it agglomerative clustering, okay? Exact same thing, just a different name. So it's .cluster agglomerative clustering. And if we look at, so it's the exact same thing, right? Syntax, you do the fit and then you get the labels. So let us now build a model for hierarchical clustering. So clustering model, and this time let's go ahead. Actually, before we build the hierarchical clustering model, let's actually see if we can create this dendrogram. It would be nice to kind of visualize that. You really won't do this in practice, but since we're doing it the first time here, So I'm going to do a little bit of syntax here to just to visualize it. So first of all, we want to generate the links. By the way, you don't have to do this for hierarchical clustering. Okay, this is just to visualize. So maybe let's say so under this, let's say visualize clusters. Visualize dendrogram. So first for that we need to do is generate links. So SciPy is another library that has some of these sort of mathematical calculations. I think sklearn probably already has it, but this is one that's commonly used. Okay, and then let me create the hierarchy. Get me all the links for X, and I'm going to use a method called ward. Ward is a way of calculating distances. And then, all right, so let me then say hierarchy. I like this library because it gives the dendrogram. Yep, it gives the dendrogram of Z, which is all the linkages, and then let's see, X label here is the cluster size, and the Y label is distance. Title, this would be dendrogram. Okay, let's see. This is a long shot. Sometimes this thing takes time. But so yeah, while that's coming up, let's go ahead and actually build the hierarchical clustering model. So that was the same syntax as before, but agglomerative clustering. So let's go ahead and borrow that code from here. Just replace k-means with agglomerative. I was hoping we could get this list, but yeah, whenever sometimes the kernel is busy doing one thing, it takes time to do agglomerative clustering. And we define here, let's see, hierarchical clustering model. Here we are going to provide the clusters, right? So we do go through the dendrogram to find the number of clusters we want, and then we provide that number of clusters here. So do a fit, and then let's call it the H plus labels. All right, so this is the dendrogram that was generated from the previous piece of code. And as you can see, so here's all the 4,000 data points. And you know, it's getting paired and paired and paired and paired, and this keeps going up all the way until you only have. So you see that you could have in distance, you know, if you you remember in the k-means it said the 2 was good, and you see that there's a big distance here, right? So yeah, 2 would have been a good number of clusters, but then you can also come down here and say, yeah, this is pretty tall as well, so maybe we'll just cut it off here, and then see, so this all would be one cluster, everything that's in this would be a different cluster, and this would be another tiny cluster here. So this cluster would be, second cluster would be very big if you go with 3 clusters, right? And all right, so if we were to do this, Okay, what's the error? Oh, no random state. So this doesn't have random state. So because there's no randomness, right? In agglomerative clustering, you're not randomly picking any points. You're actually calculating everything. So this is another example where, yes, it falls under machine learning. There's really no learning going on. It's just a calculation. Okay. All right. So now we've calculated that. So what is the silhouette score? We've got to calculate the H clust cell score is the silhouette score of X and H clust labels. And let's just look at what the H clust cell score is. 0.94. So whereas up here it was a 0.87 with, see, 3 clusters gave us 0.87 through k-means. H cluster gave us 0.9 for the same 3 clusters. And let's visualize this again. Maybe it'll help to compare this chart with what the hierarchical clustering, how did it break it into 3 clusters, right? That would be nice to see. Okay, so k-means, let's go with H cluster labels, and let's go with this hierarchical clustering. Okay. So you see how in k-means it kind of cut this off here in the middle, and you wouldn't really have said these are 2 different ones, right? In hierarchical clustering, it does a better job of putting all of these in one cluster, and then it kind of breaks this out into a different cluster, and then these are like the people that come not very often, but they spend a lot of money. So I think I would be more inclined to believe that these are better clusters than the k-means, just because of the way. And again, when does k-mean perform better? When does hierarchical perform better? If your data is very centroidal or has very good centers, like in our example, then k-means would do very well. Whenever you have data that's very much dense and has where distance to the center gives you a good indication. Whereas in this case, you don't really have any centers, so I think this does a better job of saying these all are in one. Can kind of lump these together, and these are sort of also on their own. All right, so we looked at the top-down approach, which is the k-means, the bottoms-up approach, which is hierarchical clustering. But for completeness, there's one more thing I'd like to do, and that is talk about, in many cases, what would happen. Oh, actually, we didn't go back and run. Function just to look at. So let's do that real quick. Do a function and iterate. Do that very, very quickly here. Function for hierarchical clustering. Here. Clust, and this is clustering. Agglomerative clustering is the name, and use this model to fit labels, H cluster labels. By the way, I repeat this a lot because, and I want you guys to repeat this a lot because these are things you're going to be doing quite a bit anyway. All right, so now we've defined the function. Now let's put that in a iterate over different values of k, which now, because we have a dendrogram, we probably didn't need to do that. But if you can't visualize it in the dendrogram because you just have way too many data points, then you would just do this. You just compare the cell score. So let's say cluster H clust, and let's put the cell score here. So 2 gave the best. 3 was also not too bad, right? And so I think, you know, the 3, my guess is that with 2, it would have put these 3 points also in this cluster or something. All right, so basically the winner is 2 clusters, but I think we would probably go, it makes more sense to go with 3 in this case because we know what it means, right? We know what these 2 dimensions are. Okay, now one more method I want to talk about is a lot of times you will find data that doesn't fit this type of structure where you have a centroid and, you know, there's a center, a visual center, but we as humans, we still know how to deal with it. But if we were to try to apply k-means or a hierarchical clustering, it won't work very well. So look at, think of a data that looks like this. So suppose we had data points that look like, you know, you have data that look like that, and then you had here, and then, right? So we as human beings, we would have looked and said, oh yeah, you know, I can see a gap here. And so I would have put this one like this in a cluster of its own like this, and this in a cluster of its own like this. And then if I see a point here and a point here and a point there, I'd be like, well, those obviously don't fit anywhere, right? So this is if your data doesn't have this centroidal type of, you see how these have very dense and centroid-like behavior. That means they have a center and everything is close to the center, right? And if something's farther away from the center, it doesn't belong there. Here, if we put the center somewhere here, right? Sometimes, right, if we had put a center somewhere here, sometimes these points that are out here may be too far from the center, whereas a point here on, you know, across might be closer, right? But we obviously know as human beings, when you look at it, we say, no, this point is definitely part of the second cluster here and not part of the third cluster, right? We know that. So if we try to apply k-means to data like this, then you're going to see something like this. It's going to, you know, create something that's, it'll probably create one cluster it's like this, right? And then another cluster like this, and then put another cluster like that, right? Because it's looking for centers, right? It's looking for centers. And we know that, you know, this is not right, and we don't want to do that. So there's another methodology, which is, oh, by the way, and also we definitely, k-means and H cluster is always going to try to put every point in a cluster. Right? All right, so there's another method, an interesting method, where you take, you set a small window, okay? So let's say, think of again what might be going through our minds. Let's say we take, I'm gonna zoom in a little bit here, okay? So suppose I create a window size. I'm gonna say that my window size is a small, it's a small window, right? Or it's, you know, maybe epsilon equals 0.5, a distance of 0.5. So what that would do is, so it's going to, so let's say we start with this point here, okay? And it creates a small window of size 0.5 like that, okay? And then there's another input that says the number that I need, okay? So the min, I don't remember what it was called. Let's just say it's min count, okay? And let's say that is 2. So in a window of size 0.5, if I find at least 2 other points, then that is counted as a core point in this cluster. So now, because this is part of that, now this becomes another core, and then I put a window around it. It has two. I put a window around this. I put a window around. But you see this point on the top, this point right here, only if I put a circle around it, there's no other points, right? So I'm going to color that purple, okay? And I'm going to say, okay, so that means that is an edge point. It doesn't have any. So I'm not going to keep going because it's an edge point. But then I go the other way, right? So now I have one here, and then I have one here. So it's got two. All of these have two, right? So let's say I just keep going, right? And then I keep going until I get to one that, right over here, that is another edge point. So you will end up with a few edge points, right, that don't have, that within this window, it doesn't have the minimum number to continue, okay? And that is how it captures this as one cluster. And then it does the same thing for some of the other points, right? So in this way, it would repeat the process for this other one, and this other one. And so what, as a result, what happens is you can have, data that doesn't fit into like circular densities. You might have different types of densities, like these elongated densities, right? Where you know that this point out here is really far from its center, but it really belongs to the same one. And at the same time, you might have, if you have a point like this one out here, that in its window, there's nothing. So the purple ones, it still might have at least one, right? Because it came from one of them. But if it doesn't have any, then this methodology counts it as an anomaly. Okay, so this method is called density-based spatial clustering. Okay, also known as DB-scan, right? And I really like DB-scan because a lot of times when we're dealing with data, we can't assume this, nice dense structure, or even density. We usually have data that might be more like this, and we do also have a lot of anomalies. And so DB-scan is very good at identifying or capturing anomalies. All right, so let's go ahead and build a DB-scan. Oh, by the way, in Python, whenever it creates these clusters, what it'll do is, if it finds anomalies, it'll just put all the anomalies together in a different cluster, and it'll call that cluster, it'll give it a label of -1. It'll give this cluster a label of -1. The red cluster. Okay, so all right, and we'll see that as we go in and start doing the modeling. All right. So let's say build DB scan model. Let's go with sklearn DB scan. So it's also in cluster DB scan. You see this EPS is the epsilon. This is the window size, and min samples. So that was the term I was not remembering. Min samples is 5, so it needs at least 5 points within a window of 0.5, within a epsilon distance of 0.5, for it to be considered a core point. Otherwise, it may be considered an edge point, and then if none, then it would be considered an anomaly. Okay, and the default is 5 and 0.5. So, and do they have it yet? We have an example here. Again, cluster db scan. It's a dot and labels, so exact same syntax again. So let's do what we did very quickly again here. Maybe in this case, yeah, actually, let's do that. So import db scan, yeah, all right, and then with db scan, remember we don't give the number of clusters here. We have to give the window EPS, and let's give an EPS of 0.3. The default is 0.5. And let's call this db scan. Fit labels, and let's call this db scan labels. And when we give that, we'd like to calculate the dbScan sales score. I don't expect dbScan to do very well in this one because I think the data does have some kind of centroidal behavior, but at least I think it would be nice to capture some of the anomalies, because I would say, you know, in one way you could say that all of these points are one cluster and all these out there are anomalies. dbScan should pick a lot of anomalies because there's many points here that don't have that have a large window. So I don't think it would do very well, but let's just see how it does. Okay, so we built this model. Let's look at what the sales score is. 0.9. So it's not bad, I guess. Let's visualize it and see what how did it do the clustering with that epsilon value. Scan labels, and no, so this would be scan. Okay, so okay, but not very good, right? Because we would have thought that, you know, some of these points, the window might be too small, because of which it is not, and 5 points may be too many. If we reduce the number of points it requires, so the min, what was that, the min samples, if that was smaller, then it would probably start allowing some of these other points to be part of it. But right now it's, but maybe we can change the window size and see what happens, right? Okay, so let us define a function and iterate just like we've done before. Okay, so one thing for us to know is maybe we should also calculate how many anomalies, right? That would be a good, the number of clusters and the number of anomalies would be nice, because we're not providing K here, so we still do need to know how many clusters we have. So in addition to the sales score, we want to count, let's say, db scan clusters. And so this is a little, you know, because remember the db scan labels is a, let's see what that looks like. db scan labels, right? It's an array of values 0, 1 to 0, -1, right? Let me see if I can do this. No, because it's a series. So okay, what we want to do is we want to see how many clusters. That means how many unique values you have here. And let's see. So if we say set, okay, so dbScan labels has values -1 and 0 because it's, so that means there's only 2 clusters. So if we say len of this, it should give us 2, right? And but one of them was -1, which means those were anomalies. So let's take out, let's say -1 if -1 is in db scan labels. That means I don't want to count the anomalies as a cluster. Okay? 0. So if so this is what would give me, yeah, so this is 1, right? This is what would give me my number of clusters. So I'll just put that here. And then to know whether how many, so if I said db scan labels, I want to know how many anomalies I have. If I say db scan labels, and I put it into a list form, right? That gives me, and then I want to count how many of them have a value of -1. So now that I have a list, I can do a count -1. All right, there you go. So this is the number of anomalies. So, we can call it noise or whatever. So db scan noise is this. So now that we have that, if we put this in a function, I would like to know how many clusters and how much noise for different values of epsilon. So let's clear this up and then say function for db scan def cluster db scan provide x, and we're going to provide the epsilon. And okay, so we've got, and you know, calculate the clusters and the noise and all of that. Epsilon, maybe let's say epsilon or something, just so it's not the same. Okay. All right, and we also want to make sure that we return all of that, right? So return, maybe we don't need labels, so let's just say we want db scan clusters or syscore, db scan syscore, db scan clusters, and db scan noise, right? So return that. So now that we have that, we can now put it back into a function, but here we're iterating over different values of epsilon. So let's say iterate over epsilon or best. So score and so epsilon, and these are small values. So let's give it maybe 0.1. Let's go smaller, although smaller might not help us very much. 2, 3, 5, 6. Let's go all the way up to 0.7. And db scan score. We're going to get multiple values. db scan cluster. db. Again, the naming of these could have been something else, right? If we wanted to. I'm using the same names for simplicity, but all right, cluster db scan EPS. Okay, and I want to print. So let's go with clusters. So it matches the same order we had before. So db scan cluster, db score. We didn't have to do that, but I like to keep the code easy to read. Okay, so first of all, we want to say epsilon value, and then APS, and then I want to give a tab, and then say, okay, so now we want to say clusters, and then we give db scan clusters, and then we say syscore, db scan syscore, and then we also want to see noise, right? So So cluster cells 4, and then some noise here. dbscan underscore noise. Right. I know we're a few minutes over here, but I'll just wrap this up. And then cell score. Right. So I think I didn't. dbscan cell score. Cell score noise. Oh, yeah, I think so this should be, there you go. Okay. Here. So we've got, so as epsilon changes, see the number, when epsilon is very small, makes sense, right? There's many clusters because the windows are very small. You also have a ton of noise, but the cell score is not very good, right? And then so as you go, so you see that the best cell score is around about, with one cluster, you have about 74 anomalies at epsilon of 0.3, which is what I had used in the beginning as an example. And so more than likely, it would have put a lot of these points into one cluster and then said, these are just the people that, come to the store. These are your main folks, and then you have all these anomalous people, but those are the ones that are bringing you the most amount, right? So yeah, again, the cell score here is lower. We would have probably gone with the hierarchical clustering for this example, but whenever you have data that looks like this, then that has this non-centroidal behavior, then you might want to use dbscan. And I want to show you guys just some comparison. I really like this. There's a page that shows the comparison of the different overview. Yeah, this is what I like to show. So you see here, this is the example that I was showing you guys, that when you have data like this, and so every column, so depending on the type of data, you see how each model performs differently. So if we look at the ward, which is kind of like, the k-means, this is in different k-means, you see that, it tries to put things in cluster, in like a centroidal one, right? You see here, it tries to put the bottom here into one and this top into one and that one, because it's looking for a center. But it does really well on these, right? You see that k-means does really well whenever the data is like this, which is good. dbscan doesn't do very well because these are all anomalies, they're out too far, but it does really well on this type of data. So depending on the type of data you have, you might have to go and pick. You see that whenever you try k-means with different agglomerative, by the way, here's the hierarchical one. Again, it does really good when you have data that is centered, but here again it's starting to mix up. These points are pretty close, so it would have gotten paired with some of these other points, right? And this is another interesting, when you have data that's all one big blob, shouldn't it all have just gone to one cluster? But then you see different models try to put them into different clusters because it thinks there might be a center out here. Whereas dbscan does a really good job, but it typically takes too many anomalies, and it's a balance. If you make the window too large, then it's going to start behaving like the k-means, right? So in general, k-means or agglomerative are good if your data is more centered, and dbscan is good if it's more has some other type of shape or behavior. All right. So with that, let me go ahead and turn off the recording.